Hi, geometry students. It's day 2 of Unit 6, more with Pythagorean theorem. So that starts with a little warm-up. Let's do number 1 together. So because it's a right triangle, the side opposite, that's my C. Here's our A and B. So when we go to plug right on in, it should be x squared plus 3 radical 3 squared equals 7 radical 2 squared. Feel free to use your calculator to assist here. And so on our calculators, we would want to make sure that we have parentheses. So 3 radical 3, close it up and square it. That's going to give us 27 right here. And then 7. And then radical 2, close up that parenthesis and squared. That'll give us 98 right there. All right, subtract that 27 on over. We get x squared equals 71. Ooh, not gonna be able to do too much with this. So when it takes the square root, 71, that's not going anywhere. And it doesn't say where to round, which means leave it as a nice exact answer. That is as good as that one is going to get. All right, for number 2, if you'd like to try that one out, the answer should end up x equals 6. So feel free to use that one as some extra practice. Otherwise, let's move on down to the bottom here to what is new for today. And that's called the Pythagorean inequalities. So the Pythagorean theorem is an equality. You got an equal sign in there. So when you have a right triangle, we know the legs are A and B, the hypotenuse is C, and therefore you end up with these two parts equal to one another. And now you might be thinking, why is the C squared on the front versus on the back? Well, it's all the same difference. So if you'd prefer to see it this way, write it like that. You're going to see why here in a second. We did it like that though. What happens is when you have an obtuse triangle, meaning that here's my big old obtuse angle, we're going to treat the side opposite of it as our C. So whatever the longest side is what we deal with as the C value. And what you'll see is that the two sides, no pun intended, are not equal to each other, but the C squared will end up greater than the A squared plus B squared. And when we think about an obtuse triangle, an obtuse angle itself, we know is greater than 90. So if you can kind of think about that matching. So this part is greater than this, an obtuse angle greater than 90. You can kind of see how that works together. And then go in the flip-flop of that. Here, we're still going to treat C as whatever the longest side is that you have. But if it turns out that you have an acute triangle, so all 3 angles are acute, then what you'll see in this case is that when you square C, it will be less than the value of A squared plus B squared. And if we think about an acute angle, that is less than 90 degrees. So that's kind of a nice way to think about it to kind of help make that connection there. All right, let's put this to good use now. So when we go on to this next page, it says, tell whether the measures of the side lengths can be the side lengths of a triangle, and then classify it as acute, right, or obtuse. All right, that first part actually references all the way back to Unit 1, something called the triangle inequality. And in case you're like, I don't remember that, refresher, triangle inequality says that the sum of any two sides of a triangle has to be greater than the third side, or the fast way to check is that the sum of the two shortest sides of the triangle has to be greater than the length of the third side. So that's typically the easiest way to check it. So if we use A as our example to show this, 5 and 7 are my two shorter sides. 8 would be my longest side here. Right? So what I want to do is to check to see if it is a triangle. There's my step 1. All right. We're going to just take 5 and 7, add it together, and check to see, is it greater than 8? Well, yeah, 12 is greater than 8. So we would say, yes, this actually forms a triangle. All right. Then step 2 is going to be to classify the triangle as acute, right, or obtuse. Here's the new step. So treat the shorter two sides as the A and B, the longest side as your C. All right, so let's take A is 5, B is 7, C is the 8 there. And I'm going to plug it in, and let me write it the way it looks on the first page. So C squared, we're going to compare that to A squared plus B squared. All right, 8 squared over here, we can do 5 squared plus 7 squared. This will give me 64. This is 25 plus 49. And if we do 25 plus 49, we get 74. All right, 64 is clearly less than 74. And so if I have a less than, think less than 90 would be acute. So 64 less than 74, that is an acute triangle. So you have to check first, will it form a triangle? Second, what kind of triangle? Because if it doesn't even form a triangle, I don't need to do the second piece of it here. Let's try one more together. So if I slide this on over, part B, first things first, treat the shorter two sides, 5 and 8, like I said, is like our A and B, and then I want to compare it to that third side. So 5 plus 8 is 13, which isn't greater than 17. This won't even form a triangle. If you can kind of visually think about it, if I had a side length of 17 and then over here 5 and over here 8, they wouldn't even reach. That's the problem, right? So it wouldn't form a triangle, which means you don't have to tell me what kind of triangle they form. With that being said, let's try another one where it does work out. So when we hit C, all right, first things first, check and see if it'll form a triangle. So 7 plus 12, is that greater than 16? So that gives me 19, which is greater than 16. So yes, it will form a triangle. Since it forms a triangle, now let's figure out what kind. So A, B, C. If we do C squared and we compare it to A squared plus B squared, I get 16 squared compared to 7 squared plus 12 squared. All right, grab your calculator. 16 squared is 256. 7 squared plus 12 squared is 193. So that little fill in the blank here, what I'm looking for is that 256 is greater than 193. And if the C squared portion of it is greater than this, think greater than, that would be an obtuse angle if it's greater than 90. So when C squared is greater than this is an obtuse triangle. So now we've seen a couple different cases. We saw one that came out acute. We saw one where it didn't work at all. We saw one where it was obtuse. All right, let's look at one more of these guys. So D is a perfect one here, where if we treat these as A, B, and C, you're adding up the two shorter sides, so A and B, to see if it's longer than the longest side, to see if it forms a triangle. So this will give me 23. Which is definitely greater than 17. So yes, it'll form a triangle. Now let's see what kind. All right, now let's try C squared and compare it to A squared plus B squared. So 17 squared, I think I know, but I'm going to double check. Yeah, 289. And then 64 and 225. So 225 plus 64 also comes out to be 289. So if the two sides come out perfectly equal, that's actually a right triangle, because that's the Pythagorean theorem itself. So that kind of covers the three cases. Let's save E and F for a little recap for class, and let's move on. So on to page 7. There's a lot in these notes. Pythagorean triples. This got mentioned in the day 1 notes. Pythagorean triples is when you have 3 whole numbers that make the Pythagorean, there we go, theorem true. So for A squared plus B squared equals C squared, A, B, and C are nice whole integer values or whole numbers. A lot of times you end up with weird radicals. All of these ones, you should get pretty values. So if we do 3 squared plus 4 squared, and then equals, this would be our C squared. we get 9 and 16, and then take the square root of that total, it comes out perfectly at 5. And we saw that Pythagorean triple yesterday. The rest of these all form nice Pythagorean triples as well. You can always find the last length by doing the Pythagorean theorem and plugging on in. Or if you start to memorize them, some of them are multiples of one another. So when we have like 3, 4, 5, if you double all those values, another Pythagorean triple is actually 6, 8, 10. So you can use one Pythagorean triple to sometimes find out another one. So we will come back to these and look at them in class. If you want to look ahead, feel free and see if you can figure out what those missing pieces are. Otherwise, moving on down, rationalizing the denominator. This is going to come up because we have some situations where you're going to end up with radicals in the denominator, and that's something that we would just refer to as like an improper form. So to move or to eliminate, let me say it that way, eliminate the radical in the denominator, what we're going to do here is take whatever fraction we have. So like this first one, since there's a radical 3 in the denominator, we're going to multiply this fraction by whatever radical's in the denominator over itself. So radical 3 over radical 3, because that value is really just equivalent to 1. So I'm just multiplying it by a different form of 1. When I do that, the numerator will give me 2 radical 3. The denominator would give me radical 9. And now the denominator is a perfect square, and I can take the square root of it. So what you're going to notice is that the answer doesn't eliminate the radical altogether. It just gets the radical out of the denominator. So it's perfectly fine to have it in the numerator, not in the denominator. So let's try it again. So this next one, if it's radical 2 in the denominator, we multiply by radical 2 over radical 2. That'll give us 4 radical 2 in the numerator. In the denominator, if you can already see what's going to happen, you can just go straight to saying that radical 2 times radical 2 is plain old 2. And then in this case, we can actually simplify because the numbers on the outside can reduce. So that 4 and that 2 can reduce down to 2 over 1. So I would just end up with 2 radical 2 as an equivalent answer. Now, if you're ever questioning it, you can grab your calculator. And so I'll bring mine over here. If I do 4 divided by radical 2, it's going to give me a decimal value. What I want to show is that my answer, that 2 radical 2, gives me the exact same decimal value. So same value, but now it's in more of a proper form here. No radical in the denominator. All right. If we do one more of these together, maybe let's jump down to number 6. Think about if the radical is 14, then that's what we multiply by, top and bottom. All right. This will give us 10 radical 14. We multiply those two radicals together. We end up with just plain old 14 all by itself. And then the numbers on the outside can simplify. Each of those are divisible by 2. So that would come down to 5 over 7. And then keep that radical 14 in the top. That is going to be a super helpful process to know soon. All right. Flipping on over to the last page, if you can believe it. We've got 1 or 2 more questions to look at. The top one here, let me slide down. An isosceles trapezoid. We got to find the lengths, or the lengths of the bases are 14 and 13, and the length of each of the non-parallel sides is 10. So let's sketch something here. So isosceles trapezoid meant 2 equal sides. The bases are 14 and then 30, and then the non-parallel sides are 10. Find the length of the altitude in the trapezoid. All right, well, altitude is a fancy way of saying the height. So if we drop down from maybe one of these corners here, a nice perpendicular line, this would be our altitude. Think about how this relates to the current unit that we're in. If I drop down 2 altitudes, one on each end of that base, this would essentially create a little rectangle here, which means this length has to be 14. So if the full length is 30, we could go 30 minus 14. I have to have 16 on these outside pieces, and it should be symmetrical. So if we chop that in half, it's going to be 8 and 8. I have a nice little right triangle right here. So to find the missing side of a right triangle, here's where Pythagorean theorem comes in. Now, if you were paying attention back in those Pythagorean triples, you might recognize this one right here. A hypotenuse being 10, side being 8. If you're not sure, you can throw an X in there. Otherwise, this was the Pythagorean triple that I mentioned. That was 6, 8, 10. So this side here, if you do the Pythagorean theorem, will come out 6. So the altitude is going to be equal to 6, and then it'd be inches in this case. If you're not sure, then definitely try it. All right. Let's see. Let's jump all the way down to 3. Last one on the page. If the perimeter of the square is 20, find the length of the diagonal in simplest radical form. All right, so we have a square. So 4 congruent sides, 4 right angles. That's all stuff that we know. And the perimeter is 20. So if the perimeter is 20, each side here would then be 5. All right, find the length of the diagonal. So if we draw a diagonal in, here comes that right triangle. All right, if I call this my X, these would be like the A and the B, hypotenuse of C. So if we go 5 squared plus 5 squared equals X squared, this will give us 25 and 25 for a total of 50. And then when we take the square root, we're actually going to break that right back up into 25 and then 2. And so X would be equal to 5 radical 2 in simplest radical form. All right, next time I see you, we might go back and cover a couple of those questions that we skipped. Make sure you've answered the video questions. Thanks, guys.